Packet 6, class 26. We'll go 27. So we're getting there. Thursday, 5:20. Mostly impulse today. We'll wrap up some other stuff. Let's see what we got here. Okay. What is that? There's something coming up along the bottom of the screen. Looks like some kind of wave or something. Yeah, I think it's a wave. No, wait. There's some type of structure to it. Whoa, it's a number 2. Woo! 2 more sessions. And then we keep going. What's it below? John Lennon holding up 2, saying 2. John Lennon was one of my favorites. He was a hero of mine growing up. I bawled, and I just cried and cried. And my buddy told me we both cried together the day he was shot. I think I was a sophomore, junior in college, maybe. Oh, it's horrible. Now the weather, if it doesn't rain today, and it doesn't look like it's going to, it's kind of threatening. And tomorrow it's not supposed to rain. I'll watch the master David Payne tonight, but I don't think, I think we're on, surprisingly. rain every day. I thought there's no way we're having a picnic this year, but I think we're on for a subdued kind of a smaller picnic. We're going to have 300 people out there, but we're not going to have that. But we can have a picnic tomorrow. So that's outside, means that you guys should be able to come. Even if it's inside, you can come for a little bit. So you show up about 12, 10, somewhere in there. The picnic will go to about 1 o'clock. So we'll get some pictures, big group pictures, play a little volleyball, maybe bring a blanket, bring a good book if you want, and just kind of kick back and chill, enjoy the scenery, play some bocce ball. Someone said they're bringing some cornhole. We'll bring some volleyball, bocce ball, frisbee, things like that, picnic stuff. Bring a blanket, bring a lawn chair. And tomorrow we'll eat. And if you were involved with the, you definitely want to come if you were involved with the flash off, because you get a free lunch. The other way to get a free lunch is to bring a dessert tomorrow. Get there by 12:15 with a dessert in hand, and you get a free lunch. Otherwise, it's only $3. $3 for a hot dog, and this will be maybe chili. I don't know. That adds a whole nother complication. But at least a hot dog, the fixins, right? Chips, a drink. That's probably it. Oh, and dessert, all for $3. The packet organizer, I'm still working on that. It's going to be the most detailed packet organizer I've ever made, because I'm going through and I'm looking exactly what you got to have, because it's complicated in packet 6, right? Now, you're not going to need 6, 13, 14, or 15. You can pull those off the back, or you can just leave them attached. It doesn't matter. Don't throw them away, though, because if you do the June thing, we are going to be going into those some, as well as additional stuff, but we'll definitely kind of hit parts of those. Don't forget tonight, 9 to 10, we'll do our Zoom. I'm getting ready to go to Sam's here in a little bit. I'll pick up the good dogs and all that, but then come back, eat a little dinner, then we're going to do the 9 to 10 thing. We're going over pretty much every problem on the back side, the third side of the take home, but the first 2 sides we'll go over tonight. There's that class picture I'm talking about. I want to get one like that with you guys so I can display it. It gets displayed all summer on the Facebook group and all that. Okay, next week remains pretty much the same, and nothing's really changed there. You got to have that take-home test submitted by 1:10, because at 1:10, this is, okay, this will be our last version, yes, we have this one and then Monday, but Monday, pretty much it's a live version of going through test 6B. We're going to introduce new materials. That may be an extra long one. I hate to tell you that. That may go till 2:30, but you can, part of it you can just watch the recording. But I've got to first tell what happened on Monday in class. We are going to be working on stuff, and then we got to go over the test. So the take-home test, official key. You could show up Tuesday and take the test, or you could submit it the usual, get the email, the usual kind. But if you're waiting on that, you're not going to be able to get it until Wednesday, 2 p.m. Wednesday. And then yours is due. We'll do a black and blue Zoom. That's another Zoom we'll do. That's that extra Zoom we're going to do on Thursday from 1:10 to 2, where we go over the problems, then you have it and you correct. Okay. All right, so that it? I think that's it. Yeah. All right. The Physics Hall of Fame, the final Hall of Fame, is announced via Facebook and Canvas by 11 p.m. Sunday. Now, the first semester was just straight up who did the best on the raw score of the tests. So that kind of lays a baseline, and there's 7 students that are in that Hall of Fame. Now we're going to add to that 10 more students. Normally, I do, when I first started Hall of Fame, I would do 10% of the class. So like if I have 150 kids, I would only do 15. Well, then as the years went on, it bumped up to now it's 20%. Well, at 75 kids, 20% is 15 kids. I'll go 17. I'll go a little extra. And you guys are in there as well. With you all, it's like you can't really participate in class, but how much have you participated? And all 3 of you, are very, very active on the, you're not just kind of watching the recording. Those students have no chance. But and Rose is already on there, by the way. Rose was on first semester. So, Eric and Anthony. I have it down to, I can pick 10 more, and I have it down to 20 short list. And I'll say that Eric and Anthony are both on the short list. Now the question is, of those 20, how many get only 10 of those? So how do I decide? Well, I'll spend all weekend trying to look at, I'm seeing how active are you? What are you doing? Are you the whole student I'm looking at? And it's good to have that on your resume. People do, they put in the Physics Hall of Fame. And then and I put it, if I'm writing a recommendation, I spend a paragraph talking about that and all that entails and how hard it is to get on there and how competition. So yes, it does. It is not a little deal. I've been doing it since 1986. There's the 3. We talked about this. There's the 3 equation sheets. I'm going to add a side 20 this weekend. That'll be available Monday. It'll be involving impulse, what we're talking about today. Also, I told you this yesterday. I'm selling this. I've had 3 students that are interested in it. One, though, said, okay, I'll buy it if I can have the pen. And I said, hold on a minute, Buster. That pen cost me $120, and that's practically new. So I plan on keeping the pen for my next one. Now I'm willing to negotiate. Also, if you buy this from me for $500 and the case, and if you throw the pen in, I'll give it to you for $75. Okay, that's still a bargain. $575 for everything. Then you get, I'll tell you another deal. You get free admittance into the physics June. All right, sweeten the deal a little bit. Speaking of that, June, the June project, from Gravity to Ultimate Fighting Tool. I was thinking last night, I was riding my bike around town. I was thinking, that if I'm a student and my parents want me to do something, sit around and slavatate all around the house all day. But if I'm sitting in my room and playing my video game and mom yells at me, hey, why aren't you doing anything this summer? Then I'm going to say, hey, I am. I'm doing this physics thing. I'm maybe doing this biology thing. I'm learning guitar. So it's a fairly cheap way to keep your parents off your back at minimal expense, for me anyway. You might be able to get a deal with Dr. Fournette, but for me, I'm offering 75% off for you guys. I'm offering 50% off for anybody, but you guys 75% off. So that's this summer. Today I went around and looked at 7, 8, 9. So if you want to keep up, we're going to go over the whole thing tonight through 10, 11, and then really the back, that third side. Like I say, we're doing that one. So I don't think we really need to go over that. I will, but that's not really at home. Tonight, the goal is to make a dessert. So tomorrow you come by the picnic. Okay, this came up in class because we're talking about trusses, cantilever, like types of bridges, right? And we did. In fact, number 11 on the take-home test is a truss problem where you're looking at forces, these static situations where you're trying to figure out the forces. Well, somebody screwed up, obviously. My wife and I are going to go to Florida, and I was going to get a hotel in Memphis. My first night was going to stay in Memphis. Well, we're not now because you can't cross the Mississippi River. And because of this, because right there, that thing was a hairline fracture for years, and the inspectors let it go. That people, trust me, people got fired. There's that cantilever. There's that same problem. See that angle there? There's the truss problem that we're working on, the statics. Somebody messed up on that one. They got too much. There's really some torque on that caused that to shift. And the question is, are there other areas along there? Apparently they found some more fractures, so some hairlines. So they shut traffic down. That is the consequence of not knowing your physics or not doing your due diligence. So for the next month at least, that is shut down. You're going to have to go somewhere else. So now we're going to have to go through New Orleans to get there. Here's some good news. This is Dr. Strauss. Dr. Strauss. This is from a few years ago. He is coming back. Yeah, I recognize those kids. He's coming back. He didn't come last year because of COVID. He can't come this year because you can't really have visitors. But he's in Switzerland now. He's going to be back and forth from Switzerland. He works on a Large Hadron Collider. And he will come in. There's what this screenshot he was showing. He works with this Atlas. He works underneath the ground at the, well, he didn't really go underneath the ground. He works on the lab above. But he's determining, how all these little subparticles, whenever you have these proton packs collide, you get these kind of patterns that come out. And we know what all these things are. And so all these little things mean something, and he'll talk about what that means. Well, he agreed to come back. He said, I'm going to come back next year because it's your last year. So he's going to come back in the spring of next year and give a talk. So if you're a sophomore or a junior, when you hear me say, Dr. Strauss in the hallway, you want to come in. All right. Next year, usually around April. So start checking me out. Normally I do about 15 guest speakers a year, somewhere there, 12 to 15. Hold on, I'm about out of juice. Okay, 12 to 15 guest speakers a year. He's one of them. He's always my final act because he's the best. Okay, so that's a coming. This is you tomorrow. Tomorrow we'll do this. We'll learn the spring dance. This is from a couple years ago. We'll learn the spring dance and we'll do it on the West Lawn tomorrow. It gets a little crazy. That'll be part of our picnic. We'll do the spring dance. Maybe a tug of war because I want to look at this force generator and force meter and see how well it works. Maybe. Okay, so now we're on to today's physics. This is from yesterday. I would go ahead and handwrite that one. That's not on the take-home test, but I'm really starting to like that problem. So I haven't written the test yet. I'll probably start writing it on Sunday. And I like this little problem. So that'd be probably good to have in your notes. Remember, it's open note test. We did those two yesterday. That's from 610. We did the back of the envelope on that one. We got 6 to the 21st. I looked it up. It's like 3.6706. So we're right on. We're right on. Pretty close to being. And I put this in the screenshots. And then we said you can use this to find the G of any planet and the G of the Earth. When you run the numbers on this, you get 9.81. The back we're not going to get to until June, and we'll touch on a few of those. I've already written the opening episode of June, and that is going to be, it's going to start off with this. It'll get into strings, and it'll get into gravophones and universes and how this brain theory. So we'll talk about all kinds of crazy stuff this summer. And then finally, yesterday, we did this Felix Baumgartner jumping from, a high altitude, almost 39,000 meters above the Earth. And his G, I believe, and though people are pushing back on that today, but I thought it was 9.78. A couple of Hall of Famers were arguing with me. So now I'm starting to wonder. They were saying they're getting 9.6 something. But anybody do that one? You have an answer? I don't know if you guys have an answer on that. I'm banking on 9.78, but that may be wrong. I'll obviously do this when I'm making the key up. We'll know then. Maybe tonight we can argue about it. Okay, so there's the Flat Earth Society. I want to start a group and make a lot of money off these idiots. And I'm going to call it the Deformed Earth Society. Okay. We'll sell t-shirts and hats and all this. And really the Earth is, this is the Earth, right? I mean, this will be on our t-shirt, but that's what the Earth looks like gravity wise. Now it's exaggerated, but this is not from some crackpot. This is from a website, a geophysics website actually. And it's showing how the different, okay, let's go. This is a better view. This is the more famous one. This shows the Western Hemisphere and the Eastern Hemisphere. So if we focus on the Western Hemisphere, look at the Andes here. If you're hiking around South America this summer, you're going to weigh a little more here. You're going to weigh a little more in here. The red is where you weigh the most. The blue is where you weigh the least. Now, why would that be? Anybody got an idea? Looks like the Caribbean. If you want a Caribbean cruise, that's a good way to lose some weight. You won't lose your mass, but you would lose weight on a scale. Why? My hint is this problem. This problem and a couple of things. Why would you weigh so much in the Andes and so little in the Caribbean?
You're at a lot higher elevation in the Andes.
Now, hold on a minute. Okay, stop. Hold your thought. If you say that, I'm going to say, well, wait a minute. All that does is increase the H, right? It increases the H, which means you should weigh less. G is smaller. Okay, now keep going. Why would I weigh more? I'm further away from the center of the Earth. And by the way, you're squaring it. You're squaring that denominator. So I really should weigh less on the Andes. Okay, what's your counter to that argument, Rose? I got you. You got to come back, right? Rose? Hello? Hello?
I'm thinking.
She's thinking. Sorry, I'm pressuring you. While you're thinking, let me tell you a story. I mean, there is a reason, but anyway, see this little orange spot up here in America? I am responsible for part of that. I'm responsible for boom, 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 the data right in there. Because this was 35 years ago, 40 years ago, 40 years ago. I was there, and I was as a geophysics senior in geophysics, about to get my degree. One of my last projects was to do a 3-week gravitational survey of Southern Rockies outside of Canyon City, Colorado. So I spent 3 weeks getting up in the morning, putting my boots on, and then taking a gravimeter, this machine, about a $10,000 machine, out, and very careful with it. And then it's very sensitive. And then sitting with a hood over my head, and then measuring, and then leveling it all out, and then waiting for the reading. And then it would give me how many milligals I am at that spot. Then I would pick it up, I'd mark it, map it all out. We didn't have GPS. You had to actually, on a map, triangulate, map it out, then walk 100 feet or so. I forget how far I walked, and do another one, and then do another one, and then do this day after day after day. And most of the time you're sitting around listening to nature and enjoying the, the cool breeze. It was summertime. But then my data gets thrown into all the other data. And that's why I'm part of that little anomaly there in the Rockies. Okay, Rose, back to you now. Why do I weigh more in the Andes than I do in the Caribbean? And it looks like Colombia too.
Would the pull of gravity just be weaker?
The pull of gravity must be greater if I weigh more. Remember that what's causing me to what's giving me my weight? Your weight is mg, right? Mg, and you throw your m in there. We pull the m out just to find g, but this is my weight. That's my weight. So my weight then depends on, well, g is constant throughout the universe. The mass, this is the mass beneath me. And this is how far I am from the center of the earth. So look in the Andes, look in this Chile, look in these mountains here. There's a lot more mass beneath me, right, than there is in Oklahoma. I mean, it's called orogeny. It's this as mountains form, the asthenosphere, the lithosphere and the asthenosphere, it kind of bulges into. We have this layer, this asthenosphere down here, and the lithosphere bulges into the asthenosphere. So beneath, if I'm standing on the Andes, I got more mass, and this is very dense rock. A lot of this is mafic. Well, it's meaning that it's dark, but it depends on the source of it. It could be granitic or rhyolitic, and it's very dense. So yes, I am further away from the center of the earth, but I have a lot of dense material beneath me, and that pulls on me more and makes me weigh more. On the other hand, when I go on a Caribbean cruise, I have a fairly thin lithosphere. There's the ocean, okay, there's the Atlantic Ocean, and then you have this thin and that's water. Water's 5 times less dense than land. And so the water's beneath you, but it doesn't affect you a whole lot. And then you have this thin layer, this thin lithosphere layer, and then you don't have so this is lithosphere, the asthenosphere. You don't have what you have in the Andes or the Rockies for that matter. So you weigh less. So mountains make sense that you'd weigh less. You'd have this big buildup here by Iceland because that's where Earth's being formed. Look over here in the Eastern Hemisphere. Indian Ocean is probably the lightest you'd be in the world. But then when you go to Indonesia and stuff, this is really, and that's not mountains. But the thing is, there's below the surface, a mile or so, there's this intrusion of really dense rock. And that's why you would weigh the most on Earth right there. There's a question. Where do you weigh the most on Earth? It looks like it's Thailand area, So it's kind of cool. That's geophysics for you. All right. You want to study that kind of stuff, you do what I did, geophysics. And finally, I saw this when I was looking around at some of my old screenshots. This is what I was pursuing. I was going to write a grant for this thing. It's about $2,500, and I got caught up and wrote on other things. But it would have taken me 3 years to get the money to buy this. But I wanted to. This is that thing. I have that cheesy styrofoam balls hanging from the ceiling. This is what I was trying to get. If you go to OU, they have a couple of these, and they're expensive. But this shows you G. The big G, capital G. It measures it. It uses the fiber, has a fiber cable there. There's a laser. These are very massive lead, probably lead balls there. And then I guess these are lead too, I'm not sure, but they are attracted to it. And that's that twist. Okay. Now we're ready for impulse. So let's spend the rest of the time talking about impulse. Now, this is 611, probably the last sheet we'll do. We may dab into 612 a little bit on Monday, but 611 is the last full sheet we'll do. It says, what's the relationship between, and it's only the front, what's the relationship between the change in momentum of an object related to the force put on an object? Okay, here's where Newton is a marketing genius. Newton, if Newton was alive today, he would have his, it'd be a Newton, you know, like there's Trump Water, Trump Steaks, Trump Hotel. It'd be Newton, Newton, Newton. He'd put his name on everything. Newton's laws, you know, first law, second law, third law, third law, third law. We saw how he cheated and got that third law, right? Yeah, so here we go. Newton's second law says force equals change in momentum over time, right? Well, he's not satisfied with that. He goes, hey, check it out. If I bring the time over here, I have force times time equals delta P. Aha. I'm going to call that impulse. Trademark. Impulse. And I'm going to brand it with this big cursive I. Now that's marketing. So this is impulse. Well, it turns out that impulse is a huge concept in physics. And here we are, we got, you know, around an hour to go in the year and it's finally getting to it, but that's COVID for you. This force is a vector times a scalar, a vector times a scalar is a vector. The change in momentum is a vector. Therefore, impulse is a vector, okay? Now, it's a capital cursive I. If you make it a printed I, you're going to get snickered at, okay? People are polite. They're not going to say anything, but they're going to go, oh my God, they're going to roll their eyes. So this person, where'd they go to high school? This is not impulse. This is moment of inertia. Like physics is its own language. And then for some crazy reason, I have a theory on this, but the AP exam, I guess they didn't have that font way back when in the 1960s when they built, and they make inertia, they make impulse a J. I still don't get that. We don't, we're purists. That's ridiculous. That needs to be changed. Anyway, so capital cursive I is impulse. It's just a rearrangement of Newton's second law. But that's what you call a genius. Now, if you think about it, in this class, we've gotten all the basics. And you know what? The rest of your mechanics career in physics is basically rearranging the basics. Okay, you take force. Okay, force, you get some time. Let's put them together. Force times time, impulse. What do you got? What do you got? Force. Over here you got change in position, delta x. Hey, let's put them together. Force times delta x, work. Change in work is energy. Yeah. Oh, you got some time? We throw some time in there. Let's divide the time, and we'll call that horsepower. That's it. Kinetic energy, what? 1/2 mv squared. I take mass, I take velocity, multiply by half, square the velocity, I got kinetic energy. Potential energy, mgh, mass, gravity, height. Springs, 1/2 kx squared. K is, a spring constant. X is how far it got stretched or compressed. You throw a half in there, you square the X, you got elastic energy. That's really what it is, folks. I mean, there's a little bit of a difference in you get to electromagnetics, even though on a small scale, it's a lot basically mechanics. I mean, you got to bring in you know, flux, those kind of things. There is some Gaussian surfaces. Electromagnetics gets to be a little bit hairy, but mechanics, you've got it already. You've already got the basics. You should not fear any kind of mechanics. Okay, let's keep going. This is what I'm building here is called an equation train. So in other words, all these different ways saying the same thing. So that is mass times change in velocity. If I open up the little piece suitcase, and that's a vector, and that equals mv final minus mv naught. Okay, once again, all the same thing. So all of this is the impulse train. In other words, you'll see it this way, various ways on. Oh, one more. Take it back. My bad. Let's add one more. And this is what we'll get to in June. There's something in a box that I refuse to show them. And that's where I'm going to unveil the box in June. But another way to do this is the integral. In June, we'll hit on integrals of f dt. We've seen that before, from T1 to T2. That's more of a sophisticated view of impulse. The area under a curve is what that's telling you from calculus. Okay, so that is that's my equation train. And we just answered number 2, it looks like. Oh, well, the units, right? The units. Well, it's force times time. The normal 90% of the time, the units on impulse are Newton dot milliseconds. Because most collisions, this involves collisions, right? So like clap my hands. How long are my hands together? Millisecond, thousandths of a second. Someone said today, well, what about microseconds? Okay, but no, usually there's a millisecond, at least maybe 10 milliseconds involved in the collision. Now, if it's a tennis ball with a court, that's going to be maybe 200 milliseconds. Depends on how much it collapses and then reforms. But anyway, so Newton dot milliseconds are the units. The symbol we said is a cursive I, capital I. What's the direction of the momentum vector? Well, we know that. That is in the direction of, it's just whatever direction velocity is in, the direction of velocity. Then it says, what's the direction of the impulse vector? And this messed up some of my students on an AP exam. The direction of the impulse vector is not in the direction of velocity. Remember, it is mass times change in velocity. The direction of the impulse vector is in the direction of the change in velocity. Okay. Okay. Now we got this. We got a couple more graphs to do. Yeah, we got just enough time. In class, we did 6A through 6C. We didn't get to 7. We'll maybe look at 7 on Monday. On Monday, we'll finish this sheet, and then we'll start a little bit of 12, and we'll finish the back of the take-home test. Here in a minute, we're going to do 6, and then we're going to do 13 on the take-home test. Okay, and then that'll end us for today. So 6 says how, whoa, no, we got more. We use trapezoids. Okay, let me back off. Let me go to this. There's my train, okay. But let's go to this for a second. This is your typical impulsive graph. And I'll put the screenshot up. This is from I normally do a PowerPoint, which lasts the whole hour. We're doing a 5-minute PowerPoint here. But here is a typical graph, force versus time. The impulse is that orange area, the area under the curve. That's why it's the integral, the impulse. But if say something were to hit, like I don't have it. I can grab it. I can grab stuff on my room, but I don't have it here. I'm getting ready. I'm building a show. I'm gonna build a shelf back here. I'm gonna put all my stuff. So when I do, okay, how about this? All right, these headphones, right? If I push into these headphones, there's a point at which these headphones are going to deform, and that's called this fade-in zone. And then say something were to bounce off these headphones, there's a fade in zone where it's deforming, and then it's going to reform what it was, and that's called a fade out zone. Sometimes this area here is called the deformation zone, and then this is called the reform zone, where it's growing back like a tennis ball. All right. So this actually happens to be an impulsive force. An impulsive force is this: when it's a lot of force over a short amount of time, relatively speaking. When the graph looks like this, that's impulsive. What if you want to make a lot of money, you become a safety engineer and get your own consulting, and then you spend your whole life doing this, going from an impulsive force to a non-impulsive force. The areas are the same, okay? That means that the impulse is the same in both cases. Only the yellow area, that person lived. The green represents somebody who died in a car wreck. And so your job as a safety engineer would be to get that green graph to look as much yellow as it can. So you do that by increasing the time. Well, how do I increase the time that your body's involved in a car wreck? I can think of 3 ways. I'll let you tell me. How can I make it safer for somebody in a car wreck?
Making cars bigger.
Well, that does help. Because that you just have more. You have more. I suppose metal between you and the wall. That can be good and bad. But what you're saying is basically is you got more things to crunch, and that's called a crumple zone. So that's one way. Cars now have crumple zones built in where it takes time to make that accordion. This is the front bumper of a car. It's behind the bumper actually, but it makes time to make that because it's absorbing a lot of energy. And so that increases the time. You're stuck with the area. Either the green and the yellow have the same area. I mean, theoretically. So you're stuck with the area. The only way you can do it is by increasing that base. So a crumple zone does it. What else does it in cars that they didn't have when I was growing up?
Seat belts.
Seat belts. We didn't have seat belts, and they restrain you from hit. They're more restraint, and they help, but that doesn't really help on the impulse. What else you got in cars, safety wise?
Airbags.
Boom. So this is an airbag, right? All those curtains of airbags that come out, side, front. That's one of the first memes I ever saw many years ago. Of course, Lay's potato chips, right? Half of it's air. They even have side airbags now. What the outside airbags? Come on, man. We're getting a little crazy here. But that helps. Say a person on a bicycle hits you, or a deer or something. That's to protect you there. Those come out in the order of milliseconds. Motorcycles. This is a BMW. To me, that doesn't make much sense because when you get knocked off a motorcycle, you don't all. Sometimes you do, but makes more sense for this. This is a motorcycle coat, the jacket, that when it feels a certain amount of acceleration, it blows up. And so that's people that I had a girl that rode horses, and she said, yeah, my vest is like that when I ride a horse, that it picks up and I'm falling and it just makes a big balloon. You notice this stylish model here. She's riding her bike. She has an accident, and watch what happens. See the collar? Very stylish. And boom, dig it. That's fine. Oh yeah. So see, you go from that to that, because what that does with your head is it maximizes the time, which then lowers the force, and you live. That's what football helmets do, right? When my dad played football, it was a little bit of canvas they stuck on their head and leather. That was it. So a couple of years ago, I gave a challenge to the kids, and they were to jump off the table onto the floor on their knees. And so I was telling them, okay, so now jump off the table. Well, then they agreed to do it, and I think it's crazy. But then I brought in all the cushions, see, to show. And then when you do it, it's great. You land on the cushions, you're fine, because you would break your knees if you just went your knees first to the floor. But when you bring cushions in, you survive. Until Connor Brown stands on the table. I don't know if you know Connor Brown. And I'm talking, and while I'm talking, he hadn't seen me bring in the cushions yet. He just jumps, knees first. He hits the floor with his knees. I see my career in front of me. I'm thinking he's going to the hospital. I'm done. I told him to jump, but he missed the joke before I could put down the cushion. And so he sat there, he kind of shook it off, and then he kind of got up and was a little wobbly for a while, but then he was okay. The next day, I bet when he's like 60, he'll be feeling it. Okay. So that's from the PowerPoint that we didn't show you. So back to this. So let's do this. So this, since we don't do calculus, we represent impulsive forces with triangles, because we know a triangle is 1/2 base times height. We represent non-impulsive forces with trapezoids. So this is a non-impulsive force. And it says, first off, it says on 6, this is on the worksheet, it says how much impulse, also get out the take-home test, how much impulse is represented by the following graph? Well, for a trapezoid, you could do it as 2 right triangles, and that takes forever. A trapezoid, just remember this for the ACT as well. The area of a trapezoid is 1/2 base 1 plus base 2 times height. You want to know why they're so obsessed with trapezoids? Because of this. Because impulsive forces, non-impulsive forces are trapezoidal. So you got to know the area of a trapezoid. Well, base 1 is 52 milliseconds. Notice it's milliseconds. Base 1 is 19 milliseconds. And so the height is 30 newtons. And that's it. So we multiply all together. And I'm thinking in a hurry here, I'm running out of time, down to 4 minutes. 1,068, I think. Newton dot milliseconds. Don't go changing the units. Take whatever units are on the graph. That's the typical units for impulse. Okay, so that answers that one. What's the maximum force? That's easy, 30 newtons. What's the average force? It's not 15 newtons. For the average, you do it this way. It's impulse equals F bar times delta T. So simply F bar, all you do is take the impulse and divide it by the change in time. So in this case, 1,068 Newton dot milliseconds divided by 52 milliseconds. And I think we get like 20.7. Sounds familiar. And then it says plot that. Well, when you plot that, you go to the beginning, you go up to 20.7, and you come across, and then you come down. All average forces are flat. And so this red area, this is the same area as the trapezoid. And the reason you do that is you can't put trapezoids into equations. So it has to boil down to a number. But if I needed one number for the trapezoid, I would say 1,068 for the impulse. But if I needed one number for the average force, I wouldn't say 30 because it didn't stay 30. It wasn't rectangular. I would say 20.7. Make sure, I think that's right. Okay, now you can solve this one from number 13 from the take home. Okay, we got 2 minutes and go. We'll do it together. The base 1 is 130 milliseconds. Base 2 of my trapezoid is 30 milliseconds. So the area, which is the impulse, equals area equals integral equals 1/2 of 130 plus 30 milliseconds times height, which is 40 newtons. What do we get? 3,200, right? I think they said, they were telling me in class today, it was 3,200 Newton dot milliseconds. Okay. What's the maximum force? 40 newtons. That's easy. What's the time average force? Now we say 3,200 Newton dot milliseconds divided by 130 milliseconds, whatever that is. And then it says plot it. Now, when you plot it, you come up, you come over. Let's go in purple this time. Come up, come over. It's a rectangle. Come down, and then you can shade that in. That is my average. Now, the area of that purple rectangle is the same as the area of the trapezoid. Woo! There's a lot to cover today. Monday. Tomorrow we're not going to do this because I'm going to be busy cleaning up my grill and picking up trash. We're done by now with the picnic. But there'll be no thing tomorrow. Our last one is Monday, and that's a very important one. We'll do what we did in class Monday, and then we'll do the video key. So that might go to 2:30, our very last one. I'm warning you. Questions from Rose or Anthony?
I'm taking my test in class on the 25th.
Yes.
Should I come to the black and blue day on one of the finals?
It'd be great if you did. I mean, Rose, in your case, if you didn't do black and blue, it wouldn't hurt you. I mean, you don't have to do it. I mean, I'm saying that's kids do that so they don't, flunk or whatever. But even if you flunk the test, you still got your A. So it's, it's up to you. But yeah, you could. Anybody could.
Okay.
But if you just
And
for
that's what I'll
complete,
plan to do.
good. I would love to have you there. Be fantastic. There's not much left in my room, by the way. It's all ripped up, but we're still having class in there. Okay. See you guys tomorrow. No, maybe see you in person tomorrow, but I'll see you back here on Monday.